So good morning to everyone. Good morning. Okay, fine. So what I will do is I will brief about whatever has been discussed in the last class. So very important one we have discussed is Ostwald's process. Right? So what is Ostwald's process? It is a commercial preparation of nitric acid. Right? It is the commercial preparation of nitric acid where ammonia will be oxidized to respective nitric oxide and water. That is first step where ammonia will be oxidized. So I'm not going to worry about balancing and all because it's a just brief explanation. Fine. So that's where condition can be around 500 Kelvin. Condition can be around, temperature can be 500 Kelvin. Then with respect to pressure, it will be 9 bar pressure. With respect to pressure, it will be 9 bar pressure, much less compared to Haber's process, right? Now, another important condition is catalyst, that is platinum or rhodium gauze. They will not use the powder, they will use the gauze. Gauze means like a cotton fibers. So that's where we have the platinum or rhodium gauze, mesh type this one, okay? So this is first step and this is the reaction condition. So next step here it will be oxidation of nitric oxide to NO2. Oxidation of nitric oxide to NO2. And last step will be treating of this NO2 with water to form nitric acid. Now important point here is whatever we are going to get, it is 68% by mass of nitric acid. How much it will be? 68% by mass of nitric acid. To obtain or to increase the concentration, these reaction at the end it has to be passed through sulfuric acid, or it should be done in the presence of sulfuric acid. So which is a very good dehydrating agent. So where we can go up to 98% of HNO3. Fine. So that's where we have the Ostwald's process. What is the advantage of Ostwald's process? Ostwald's process advantage here is whatever nitric oxide which is formed at the end, it can be reutilized in the second step. So that's where all the products, they will be utilized. Fine. That's where we have the Ostwald's process, which is meant for the commercial preparation of nitric acid. Now next we have discussed about properties of this particular nitric acid. Now when it comes to nitric acid, as we know, it is a strong oxidizing agent. Why nitric acid should behave as a strong oxidizing agent? That is due to the highest oxidation state. That is due to the highest oxidation state of the nitrogen, that is +5. So therefore it will behave as a strong oxidizing agent. So this one we have discussed with respect to HNO3 as a strong oxidizing agent. Can anyone tell me by using which reactions we have confirmed? So that is with respect to, yes, it is a strong oxidizing agent, yes, HNO3. And these things we have discussed about with some of the reactions. So which is that one? So which are those reactions? Anything? That is with respect to metals and non-metals, right? For example, we had zinc, which will get converted into zinc nitrate. It will convert zinc to zinc nitrate, NO3 twice. Same way, copper to copper nitrate. So what I mean to tell here is from zero oxidation state, they are getting converted into +2. That shows the strong oxidizing character. So not only metals. And very important one is with respect to dilute HNO3. Zinc is going to give nitrous oxide, and with respect to copper with dilute HNO3 it will form nitric oxide. So that's where they have the difference with respect to zinc and copper. And aluminium will be non-reactive because it will form a layer of aluminium oxide. Aluminium with strong acid, it will be non-reactive due to the formation of layer of aluminium oxide. So that's where we have the metal. So if I take carbon, so HNO3 will oxidize carbon into anyone. HNO3 will oxidize carbon into carbon dioxide, right? So it will oxidize carbon into carbon dioxide. Sulphur, if I take, it will oxidize that one into sulfuric acid. So that means from 0, it is becoming plus 6. Carbon from 0, it is becoming plus 4. All of them, they are going for highest oxidation state. All of them, they are going with highest oxidation state. For example, sulfur, highest oxidation state is plus 6. Same way, if I take phosphorus, that is white phosphorus, if I treat with HNO3, this white phosphorus will become H3PO4, that is orthophosphoric acid, plus 5, highest oxidation state of the phosphorus. So these are some of the reactions which talks about oxidizing character of nitric acid, oxidizing nature of nitric acid. Okay, so they are a bit important, but when it comes to Oswald's process, it is very, very important, no doubt. Fine. So we'll come to next one. That is, I will mention it as very important. Even your salt analysis, you will be doing this one. That is brown ring test, and I think it is very important with respect to salt analysis, where we have to show the result whatever we have got to the examiner. Depends. It depends on the examiner. Fine. So that's where we have the brown ring test. First thing, why it should be called as a brown ring? Because there will be formation. If you consider this one as a test tube, so there will be formation of a layer. Double layer will be formed because we are going to use the sulfuric acid here, which helps in the formation of the layer. Only thing here is that sulfuric acid should be added very slowly from the side of the tube. Okay, so it should be added from the side of the tube. Then the ring formation will be very clear. So now when the reaction will happen, there will be formation of brown ring at this particular layer. Fine. So that's why it is called as brown ring, because test tube will be round, right? So ring will be round in shape. Therefore it will be called as brown ring test. Now brown ring test is meant for the detection of nitrate. For the detection of nitrate. Fine. So now it may be from nitric acid or any other salt, but it will be for detection of the nitrate in a given solution. Fine. So that is the intention of the brown ring test. Now we have nitrate. We'll go with ionic equation. So we have nitrate. If you take HNO3, that's fine. But anyway, HNO3 will be dissociated as H plus NO3 minus only, because nitric acid is a very strong acid. So it will not remain as HNO3. When it is added to the water, it will get immediately dissociated as H plus and NO3 minus. So that's where we have the NO3 minus and H plus. Fine. Now please remember, this reaction will be carried even in the presence of sulfuric acid also. Now there will be presence of iron Fe plus 2. Fe plus 2 means ferrous or ferric. Any one of you. Fe plus 2 is ferrous or ferric. Any one of you. It is ferrous. So there will be utilization of ferrous iron. There will be utilization of ferrous ion. Okay. Now nitrate, since it is an oxidizing agent, since nitrate is a oxidizing agent, it can oxidize ferrous to ferric. It can oxidize ferrous to ferric, and itself it will get converted into nitric oxide. Itself it will get converted into nitric oxide. So NO3 minus. So what is the oxidation state of nitrogen? It is nitrogen. What is the oxidation state? It is +5. Already we have discussed. Here it will be +2. So that means it's a redox reaction where nitrogen is getting reduced from +5 to +2, and iron is getting oxidized. So that means Fe+2 is getting converted into Fe+3, means there will be losing of how many electron? 1 electron. It's going to donate 1 electron. Right? Now when I am talking about NO3 minus to NO, so from +5 to +2, how many electrons it should gain? It should gain 3 electrons. It should gain 3 electrons, right? So to balance the number of electrons, we have to multiply this one by 3. So we have to multiply Fe+2 and Fe+3 by 3. So NO3 minus H plus 3 Fe+2 getting converted into 3 Fe+3 and nitric oxide. Fine. So why we have to multiply these things by 3? Because there is 1, here it is 3. So you should multiply this one by 1 and this one by 3. So therefore this will remain as it is, but this will become 3. So that's where we have balanced with the number of electrons, right? So now since there is a H plus, there should be addition of water on the opposite side to balance the H plus. Okay? Now we will see whether charges are balanced. Now more and R +6 and -1. Total +6 and +1. So total +7 charge and -1. So therefore it will be +6 charge. Right? But on the other side we have the +9. We have the +9. So what we have to do? Any one of you? We have to make here +9 and there is already +9. So what we can do? Any one of you? Fast. So because here it is 3 2 just 6 plus 1 plus 7 is there, minus 1 is there, net charge is +6. Okay, someone had written. Yes, we have to make it as 4H plus. Now what will happen? When I will write it as 4H plus, so Muralla +6 +4 +10 and -1, it will be +9. Yes, it's balanced, but hydrogen has to be balanced, so we will make it as 2H2O. So that's where we have the redox reaction. This is not end, okay? So this is an example for redox reaction where nitrate is a very strong oxidizing agent converting ferrous to ferric, and itself it is getting reduced to nitric oxide. Fine. So that's where we have the first step. Now whatever leftover Fe+2, whatever leftover, please remember we have to add this one in excess. We have to add ferrous solution in excess. Okay, so we should be liberal. So whatever nitrate is there, it will get consumed, but still there will be some more Fe+2 left over in the solution. So that Fe+2, which will be normally in complex with water, that means which will be normally in complex with water, so therefore there will be FeH2O6. Say for example, since there is a sulfuric acid, since there will be sulfuric acid, this can be with sulfate. Counter ion can be sulfate since plus 2 is there. Since I have not mentioned, I am going as that of in your textbook. Will not mention anywhere sulfate. So in that case, I am going to have FeH2O6 plus 2. That means hexa aqua iron 2. What can be the name of this one? It can be hexa aqua. In coordination compound, aqua also we can write. So coordination compound water can be written as aqua. Okay? So iron 2. If sulfate is the counter ion, then we can write it as hexa aqua iron sulfate. Okay? So that's where we have the molecule. Now, in the presence of whatever nitric oxide is formed there, whatever nitric oxide is there, so it will take up that nitric oxide and it will become FeH2O5 NO. So that will be plus 2 and one water molecule will be released. So this is the one which will be brown color. This is the one which will be giving brown color. So that is okay. H2O5 inside of the hydrogen. So 5 should be outside. So that's 4. We have penta aqua or penta aqua nitro iron, whatever sulfate, if it is that sulfate. Fine. A comes first, therefore before nitro A can be written. So penta, anyway, don't worry about name of this molecule. Penta aqua nitro iron. So that means there is the addition of nitro, that is nitric oxide. And it cannot be called as nitric oxide, we will call it as nitro. Fine. So penta aqua nitro iron 2. So that's where we have the brown ring which will be formed. Now where is actually sulfuric acid? Sulfuric acid, nowhere it is there, right? So in reality, sulfuric acid is not involved in the reaction, because whatever acidic condition is there, HNO3 can only provide if you are using HNO3. If you are using any other salt, then sulfuric acid is the one which will provide the acidic environment. Fine? So that is one thing. And sulfuric acid, if you are using HNO3, sulfuric acid will have one role, that is, it helps in the formation of the phase, or where we can have the ring exactly at the mid of the reaction mixture. That is due to the formation of the two layers. So which will be provided by sulfuric acid. Fine, that's where we have the brown ring test. So why brown ring test will be done? To identify the presence of nitrate ion. So that nitrate ion can be from any salt, or it can be from nitric acid. Fine, anything, but there should be nitrate. So now what will happen? Nitrate, since nitrogen is the highest oxidation state, it will oxidize Fe plus 2 to Fe plus 3 in the presence of acidic condition. Fine. So there will be formation of nitric oxide. Since we have taken ferrous solution in excess, all the ferrous ion will not be utilized. There will be leftover ferrous ion, so which is going to be in complex with water, so which will take up one of the nitric oxide, which will take up the nitric oxide which has been formed due to the nitrate. So that nitric oxide along with aqua complex, it will give the brown ring. Fine. So that's where we have the brown ring, which is due to penta aqua nitro iron 2. That Roman 2 indicates plus 2. Oxidation state of the central metal atom. Fine. Everything is clear. So that's why it is called as brown ring test. Any doubts? Shall I move to the next one? Anyway, these things you will be performing in salt analysis. Please remember. And you have to mention about brown ring test, whether you perform it or not, it should be there in your answer script. Okay, so I'll submitting practical this one. So that's where we have the brown ring test. We'll move to the next one. So that is allotropes of phosphorus. So when it comes to allotropes, I will mention this one as important, not very important. I will mention it as important. So that is allotropes of phosphorus. 1 mark question from this part you can expect. Hagadre, before going to the explanation, what do you mean by allotropes? I have only taken the class for some of you with regard to allotropes of carbon, right? In first year. So what do you mean by allotropes? I can tell, okay, any other answer I will wait, so that you will take some time for typing, right? Isotopes are different, allotropes are different, no doubt. Any answer? So allotropes means these are the different forms. These are the different forms of same element. Different forms of same element. For example, very common one I will take, carbon. So we have graphite, we have fullerenes, then we have the diamond. All are made up of carbon, but having different structure, having different properties due to difference in their structure. Therefore, they are called as, or we can, in short, we can call it as different forms of the same element. Diamond, graphite, all are made up of same element, that is carbon, but they are having totally different property related to physical properties. Chemical properties will be almost same. Why? Because they are having same element. Same logic is applicable for allotropes, right? Means allotropes of phosphorus also. So these are the different forms of the phosphorus. Naturally, they will be differs in their structure, how they will be arranged, and due to that, they differs in their physical properties. Okay, and some of the chemical property, yes, they may differ due to the difference in their structure, but since they are made up of phosphorus, whatever reaction or specific for phosphorus, it will be there. Fine. So that's where we have the allotropes of phosphorus. So what I will do here is, I will make 3 columns to make you it is easy. So first one is white phosphorus. So we have total 3 allotropes of phosphorus. So white phosphorus, then red phosphorus, then black phosphorus. So that's where we have the 3 forms. So now with respect to exact color, red will be not in the red color exactly, but similar to that one. But this will be white only. Now what is that difference? I can tell that white phosphorus is poisonous. White phosphorus is poisonous, highly poisonous. Someone has written, I think. So white phosphorus is poisonous. Yes. So white phosphorus, it is poisonous. That is because it is highly unstable, or I can tell it is unstable, because of which it will be very reactive. Because of which it will be reactive. Question can be, name the allotrope of phosphorus which is poisonous in nature. Then you can mention one word, white phosphorus. Fine. So that molecular formula for this one will be P4. Molecular formula for this one will be P4. Please remember, no one will ask you to write, but anyway, it will be having tetrahedral structure where 4 phosphorus will be attached to each other. Okay? And where there will be bond angle of only 60 degree. And due to less bond angle, that might be the reason why it is highly reactive. Okay, due to the instability in its structure. So that's where we have the white phosphorus. That is one story. When it comes to red phosphorus, they are non-poisonous. They are non-poisonous, no doubt. Now when it comes to reactiveness, they are less reactive. They are less reactive, and very important one is they are polymeric in nature. They are polymeric in nature. So here it is poisonous, unstable, so because it's highly reactive, and P4 is the formula. But when it comes to red phosphorus, non-poisonous, less reactive, and polymeric structure, where P4 will be attached to each other. So where P4 will be attached to each other. That is with red phosphorus. Now when it comes to black phosphorus, so in black phosphorus we have two types, alpha and beta. Okay, so we have two types of black phosphorus, that is alpha and beta. Now when it comes to alpha black phosphorus will be having monoclinic type of crystal structure, rhombohedral or monoclinic. You people are going to discuss this one in your solid state topic, rhombohedral or monoclinic type of unit cells with respect to crystal structure. So monoclinic type of unit cells in its crystal structure. That's where we have the alpha black phosphorus. So now when it comes to beta, they will form flaky layered structure. They will form flaky layered structure. Flaky means just like I can tell graphite type, where layer by layer it will be arranged. Similar way for beta black phosphorus also. Now, which one, Ravikant, you are asking? Which one as poisonous? Whether you are talking about black phosphorus or white phosphorus. Highly poisonous one is white phosphorus. No other allotropes of phosphorus are so much poisonous. This is non-poisonous. Fine? So that's where we have the alpha and beta. This is related to difference. Okay? Just to make you understand. Fine? So that's why I made it into 3 tables. Now I will come to some of the reactions. Now very important point here is addition to white phosphorus, which is unstable, it will be flammable. It can be flammable. That means it can catch the fire. It can catch the fire when exposed to oxygen. It can catch the fire when it is exposed to oxygen. Okay. So now what will happen here is we have the white phosphorus. When it is treated with oxygen, it will liberate white fumes, dense white fumes of phosphorus pentoxide. It will liberate phosphorus pentoxide. Okay? So that means P4O10. So you are telling pentoxide. Yes. Empirical formula will be P2O5. So therefore it can be called as phosphorus pentoxide. Fine? So we have to make it as 5. So therefore it will give dense white fumes. Which one? White phosphorus. No other allotropes of phosphorus will give similar reaction. It is applicable for white phosphorus. And another very important reaction, even that one I am going to discuss with respect to phosphine. Now here I will not discuss, but same reaction we are going to discuss in preparation of phosphine. That means white phosphorus when reacted with hot NaOH solution. Hot NaOH solution, it will give rise to phosphine. It will give rise to phosphine. Anyway, this reaction we are going to discuss with respect to preparation of phosphine. Okay? So that's where we have the condition, reaction. Some of the reaction meant for the white phosphorus. And very important one is it is flammable. That's where it is highly unstable. When it is exposed to the oxygen, immediately it will release dense white fumes. That is due to the phosphorus pentoxide. 1 mark question you can expect. 1 mark question you can expect. That is, name the compound responsible for dense white fumes when white phosphorus is exposed to atmosphere. Then you should write only one word, that is phosphorus pentoxide, or you can write the P4O10 formula. You can write the formula. Fine. So that is with respect to white phosphorus. Now when it comes to red phosphorus, this red phosphorus will be formed from the white phosphorus only. Now when white phosphorus is heated to somewhere nearly, if I am right, 573, approximately 573 Kelvin. If I heat it in the inert atmosphere, that means there should not be any gas, means inert atmosphere. So that's why white phosphorus, when heated in the inert atmosphere, then there will be formation of red phosphorus. So red phosphorus is derived from white phosphorus only. Fine. Now same way it is applicable for black phosphorus also. Now when it comes to alpha black phosphorus, it will be formed when red phosphorus is heated, I think approximately 800 Kelvin. We can make it as 800 Kelvin approximately. In a sealed environment, it will get converted into alpha black phosphorus. Alpha black phosphorus. So that means alpha black phosphorus is derived from red phosphorus. Okay. Now when it comes to beta, so now beta black phosphorus will be formed when white phosphorus is heated to somewhere around 470 Kelvin. Okay, and under pressure, you should apply the pressure, then it will get converted into beta black phosphorus. Beta black phosphorus. Fine. Any question you can be expected in your exam. Normally, they have not asked right to difference between these allotropes. They have never asked. But 1 mark question. Name the poisonous allotropic form of phosphorus. Then white phosphorus. Name the polymeric allotropic forms of phosphorus. That is red phosphorus. Right? Or they can ask with respect to black phosphorus. Right? So what I mean to tell you is, when it comes to allotropes of phosphorus, that's where we have the white phosphorus, red phosphorus, black phosphorus. So white phosphorus is having formula of P4. It is having formula of P4. And very important property is it is poisonous. Okay? Because it reacts with the lung proteins and all. It is poisonous. And it is unstable. Due to that, it is reactive. Very reactive. So immediately it can catch the fire. It will be flammable. That is due to the reaction of white phosphorus with oxygen to form dense white fumes of phosphorus pentoxide. Fine. Now with hot NaOH, it will provide phosphide. Reaction is important. We are going to discuss this one in next another 2-3 minutes. That is related to white phosphorus. So when it comes to red phosphorus, since it is polymeric in structure, naturally it should be less reactive because it is polymeric. So it should be less reactive. How this red phosphorus will be formed? Red phosphorus will be formed from white phosphorus only. When white phosphorus is heated to approximately 573 Kelvin in an inert atmosphere, then that's where red phosphorus will be resulted. Fine. Now comes the black phosphorus. So when it comes to black phosphorus, there are two types, alpha and beta. So when it comes to alpha, it can have either rhombohedral or monoclinic type of unit cell. Anyway, we are going to discuss unit cell and all in solid state. And it will be formed when red phosphorus is heated to approximately 800 Kelvin, alpha black phosphorus will be produced. Now when it comes to another category of black phosphorus, that is beta, which will have flaky layered structure, where it will be produced due to when white phosphorus is heated to 470 Kelvin under high pressure, that will be resulting in beta black phosphorus. Some report tells that beta black phosphorus can conduct the electricity, but alpha black phosphorus, they are poor or non-conductors of electricity. Anyway, we are not going to detail. Now another very important one, very important in the sense property. White phosphorus will be having chemiluminescent property. That means whenever it is exposed to light, it will have luminant properties, which is not shown by any of the phosphorus, allotropes of phosphorus. That is called as chemiluminescence. Okay, so that's where we have the property of these allotropes of phosphorus. Any doubts? Any doubts to anyone? One more question from this part you can expect. Okay? Even they can ask. That's what I told, right? What will happen when white phosphorus is exposed to atmosphere? So that means, since it is flammable, it will catch the fire, or there will be liberation of dense white fumes of phosphorus pentoxide or P4O10. Fine. We'll move to the next one. Next one is related to phosphide. Next one is related to phosphide. Now, one reaction I can tell which can be important, that is preparation of phosphide. Laboratory preparation of phosphide. So as I told, phosphine will be prepared by one of the method where P4, that is nothing but white phosphorus. So when treated with NaOH, okay, there will be formation of PH3 and sodium hypophosphide, and then there will be formation of sodium hypophosphide, NaH2PO2. Fine. So that's where there will be formation of the sodium hypophosphide. From that time is called sodium hypophosphide. Okay. So now, one molecule help we should take. One of the molecule help we should take, because we cannot balance this equation. That molecule will be water. We should take the help of water to balance this particular equation. Now you can try it out to balance this particular equation. First, balance. Okay, first we will go with sodium. Sodium is already 1. Then less occurring, next will be 2, 1, and almost they are same. Yes, even phosphorus comes in 3, this one. Even hydrogen comes in, hydrogen 4. Then oxygen comes in 3. Either we should go with phosphorus or oxygen. So when it comes to oxygen, it looks like it is balanced. But phosphorus, it is not balanced, right? So what we can do here is, we can go with 2 and 2. We will see what will happen. Or will I try to avoid to disturb the sodium. We will try to avoid the disturbing the sodium. Okay. We will try to make it as 3 here only. Now we will see what will happen. So 3, 1, 4. Now hydrogen is 3 3s are 9 and 2 11. So here it is 4. No, we have to disturb sodium. No other way. Otherwise we cannot balance this particular equation. Right? So next digit will be 2. Next digit we cannot go with 1, so we have to change. Next number will be 2. So here also we will make it as 2. Here if it is 2, here also we should make it as 2 to make the phosphorus balanced. Fine. Now we will check it out. 3 2 is 6. Here it will be 4. Anyway, we can make it as 2. So in that case, phosphorus is balanced. Sodium is balanced. So 2 2 is 4 oxygen. Oxygen is balanced. So 2 2 is 4 plus 2, 6 hydrogen. Okay, hydrogen is not getting balanced. So that means 2 will not work out. 2 is not going to work out. So we will move to next number, that is 3. So that is 3. So if 3 is the number, here also straight away we should make it as 3 to balance the sodium. Now we will see. 3 plus 1, okay, phosphorus is balanced. Now sodium is balanced. Oxygen 3 2 is 6. So more one left. Okay, here we have to make it as 3. So I think I think it's balanced. Yes, equation is balanced. Fine. So it's a very important equation you can expect. So that is preparation of phosphine from white phosphorus, or write the reaction when white phosphorus is treated with sodium hydroxide. Fine. Now in this case, whatever phosphine we are going to get, it is not flammable, but sometimes there will be contamination of P4 in the product. Some white phosphorus may not be utilized, so it will be left over. So now it will become flammable when exposed to the atmosphere. So to avoid the contamination of P4, to get the pure form of pH3, so to avoid contamination of non-reacted P4, contamination of P4. So next here it is, whatever pH3 or whatever product is there, it will be made to react with hydrogen iodide. It will made to react with hydrogen iodide. Now this is another example for Lewis base character of phosphine, like ammonia. This reaction can also be an example for Lewis base character of phosphine, like ammonia. Now what will happen? If ammonia would have been there, we should have got ammonium iodide, right? So here also phosphonium iodide, pH4. We will get phosphonium iodide. So that's where we have the phosphonium iodide as the product. Fine. So we have got pH3 at least. Now that pH3 also got consumed. What is the use? No, step is not over. Reaction, you can expect this one. The whole process they have not asked. To make you understand, I am writing all these steps. Fine. Reaction, it will be the only one where if the question here is write the reaction involved when white phosphorus is treated with sodium hydroxide. This is the only single reaction you should write. Don't worry about next step. So it is there in your textbook also. So here this reaction is also example for justification for Lewis base character of phosphine. So that's why we are going to get phosphonium iodide. Now we will get back the phosphine when this phosphonium iodide is treated with potassium hydroxide. Right? So 1H plus, don't write this one, 1H plus from here, OH minus from there, so there will be H2O. Then K plus I minus, that's where potassium iodide. So what is left over? Left over is pH3. Left over is pH3. So that's how contamination of white phosphorus can be avoided. Right? So that 1 mark question we can expect. But they have not asked until now. So question can be, name the reagent used to avoid the contamination of white phosphorus during the preparation of phosphine using white phosphorus. Right? So then this should be the steps. That reagent is hydrogen iodide and potassium hydroxide. Whether I am clear? So that's where we have the phosphine. That's where we have the phosphine. Any doubts in this? Any doubts are there? Okay, fine. So in that case, another property or another way here is when phosphine is treated with metal salt. So that's where it differs. When it comes to ammonia, it was ammonia solution. So it was ammonia solution which used to be treated with metal salt. Say for example, fine. Okay. Now when it is treated with phosphine, what reaction it was there with ammonia solution? What was the reaction with ammonia solution? If you recollect, copper sulfate with ammonia solution. Not NH3. What is ammonia solution? That is ammonium hydroxide, right? We used to get copper with ammonia, right? So here it will be another product used to be there. I am talking about that reaction where zinc sulfate and all they have used, right? So in the case of the copper, it used to be copper plus 2, but here it is already plus 2. And when it is treated with phosphine, so it's going to form phosphide, respective phosphide, copper phosphide will be the product, right? Now I am talking about phosphide, which is same as that of the nitrite. Now you should tell me, what do you mean by nitrite? I have told. So this is phosphide. It is same as that of the nitrite. Only thing here is phosphide is related to phosphorus, nitrite is related to nitrogen. So what are nitrite? What is nitrite? Don't get confused with azide. N3 minus is azide. I am talking about nitrite. Anyone? Nitrite. So nitrite is a compound where nitrogen will be with -3 oxidation state. Then those compounds can be called as nitrite. Normally it will be with metals. Phosphides are those compounds where phosphorus will be with -3 oxidation state. I have copper sulfate. When it is treated with phosphine, I am going to get copper phosphide. You should tell me the formula. CuP. I will write only CuP. And another product will be H2SO4. Another product will be H2SO4. Now, what should be the formula for copper phosphide? It's not a redox reaction. Please remember. It's not a redox reaction. Whatever copper oxidation state is, that same thing will be maintained in product also. Whatever oxidation state of phosphorus is there in phosphine, same will be maintained in product also. So what should be the formula? That means -3 and +2. Cross multiply. Cu3 P2. So that's where we have the copper phosphide or cupric phosphide. Anything is fine. That's where we have the reaction with metal salt. That's where we have the reaction with the metal salt. Fine? All of you have understood? Any doubt? So this is related to phosphine. This is related to phosphine. Properties of phosphine. That's where it differs from the ammonia. Please remember. That's where it differs from the ammonia. But if you take reaction of phosphine with hydrogen halides, it is same as that of the ammonia, right? So ammonia plus hydrogen iodide, it will give ammonium iodide. Same way phosphine with hydrogen iodide, it will form phosphonium iodide. That's where we have the similarity. But when it comes to metal salt, it differs from the ammonia. That shows the strong basic character of ammonia compared to phosphine. All of you have understood? Now we will come to next one. Compounds of phosphorus. That's where we have PCl3 and PCl5. So I will mention this one as important. As I told, P block element, that is the major problem. 3 marks, 4 mark question, we can tell this can be the one. But when it comes to 1 mark, there can be variation. Any question they can ask. Right? So that's where we have PCl3, PCl5. Now, why I have made it 2 column? Because to make it easy to understand what is that different reactions. But which is meant for only one, that one I will write separately. Okay? For example, PCl3, when it comes to preparation, when white phosphorus is treated with chlorine, it can give rise to PCl3, another property of white phosphorus. Right? White phosphorus when treated with Cl2, it will form PCl3. Whether it is balanced? No. White 4 phosphorus is there, I will make it as 4 for time being. So in that case, here I am going to get 3 4 that 12 chlorine. So I should make it as 6. So this is the reaction. Fine. Now, same white phosphorus, when treated with chlorine, it will form PCl5. It will form PCl5. Many students, they are scolding now. What happened to this, Raghavendra sir? White phosphorus with chlorine, PCl3. White phosphorus with chlorine, PCl5. What is happening? But observe the concentration of chlorine. Fine. So here it is 4. That means 20 chlorine. So here I should get 10. That means PCl3 formed when low concentration of chlorine treated with white phosphorus. PCl5 will be formed when high concentration of chlorine is treated with white phosphorus. That's what you should be observing. That's what you should be observing. Okay? All of you have understood? Fine? So next one. Another reaction of white phosphorus. See, overlapping. White phosphorus, here also white phosphorus. Another reaction is when white phosphorus is treated with SOCl2. SOCl2. Please remember, SOCl2 means thionyl chloride. I think somewhere I told you are going to discuss this one in some topic I had told. I think if I am right in organic chemistry, right? So this is thionyl chloride. In haloalkanes and haloarenes, yes. And I told you are going to come across this molecule in P block element. That's what I told. So SOCl2. Many people they will write sulfonyl chloride. No, it's not sulfonyl chloride. It is thionyl chloride. Fine. Sulfonyl chloride means where any alkyl group it is attached to SO2Cl. SO2Cl. So here it is SOCl2 and nothing else is there. Therefore it is thionyl chloride. Fine. Now one of the product will be PCl3. One of the product will be PCl3. Okay. Can you guess another product PCl3? Okay, very good. SO2. Any other product? Until here you are absolutely right. But another one product is there which you have to remember. That is S2Cl2. Okay? Sulfur monochloride or S2Cl2. Why sulfur monochloride? Here it is 2 chlorine is there. But empirical formula, if you take SCl, so sulfur monochloride. Fine. So that's where we have the sulfur monochloride. If you don't remember this one, you can simply write it as disulfur dichloride. Fine. So S2Cl2. We have to balance the equation. Fast. Okay, 1 minute. First very important point here is make it as 4. Phosphorus, make it as 4 straight away. We will see what will happen. Now chlorine will become 12 and here total 14. Where it is only 2. Then if it is 2 here, then if you make it as 7, then here it will be 3. Sulfur will be 3. We have to make that one also 7. So in that case, 5 plus 2 will be 7. Don't write anything. So 5 plus 2 will be 7. So 10 is oxygen. And here it will be 7. No, 7 will not work out. 7 is not going to work out. So we have to go to next number. We have to go to next number, that is 8. If I take it as 8, then straight away I should make it as 4 here, because 4 2s are 8. Oh, I think balanced. Okay, chlorine. So, okay. Oh, okay, here we have to make it as 2. Sulfur is also not balanced. Done. Balanced. Fine. So this is the balanced equation. This is nothing but a balanced equation. Fine. Now, when it comes to other side, white phosphorus, when treated with SO2Cl2, that is nothing but sulfuryl. SO2Cl2 is nothing but sulfuryl chloride. That's why when white phosphorus is treated with thionyl chloride, you are going to get PCl3. When white phosphorus is treated with sulfuryl chloride, SO2Cl2. So SOCl2 is nothing but thionyl chloride. SO2Cl2 is nothing but sulfuryl chloride. So now you are going to get one of the product as PCl5 and another product should be as usual, that is SO2, and no other products like in here. S2Cl2 is there, right? No other product. So balance the equation. So first straight away make it as 4 PCl5 to make it P equal. Fine. So if that is the case, now I am going to get 4 5 are 20. So here I should make it as 10, because 10 2 are 20 to make it chlorine. Now we will see. Oh, okay, fine. Sulphur, here it should be written as 10 then, 10 SO2. Oh, done. It's balanced. This equation is balanced. Right? So these are some of the reactions which shows the difference between PCl3 and PCl5. Fine? So where preparation, I am talking about preparation. When white phosphorus is treated with chlorine, low concentration of chlorine, it is going to form PCl3. The question can be, this was asked, name the product formed when white phosphorus is treated with low concentration of chlorine. Now the answer should be PCl3. You can just write molecular formula or name of the molecule, anything is fine. But that one word will fetch you 1 mark. So the same white phosphorus with high concentration of chlorine, it will form PCl5. So this question was there for 1 mark. Fine. So next, when white phosphorus is treated with thionyl chloride, that is SOCl2, it's going to form PCl3, sulfur dioxide and sulfur monochloride. But the same white phosphorus, if it is treated with sulfuryl chloride, now we are going to get PCl5. Now we are going to get PCl5. Okay? Anyway, I will stop here. In tomorrow's class, once again, we are going to discuss difference in these two with respect to their chemical properties. That is also a bit important. With respect to that chemical property, there also I will do the same thing. I will make it 2 column and reactions we are going to discuss. Fine? Any doubts? Whatever we have learned today, any doubts? We have learned in the sense I can tell that whatever I have taught. Any doubts? Oh. So, white phosphorus or allotropes of phosphorus, you can expect 1 mark question, anything it can be. And with respect to PCl3 and PCl5, you can expect the question. And another important reaction what I told is white phosphorus with sodium hydroxide, hot concentrated sodium hydroxide. Fine? So that's where there will be formation of phosphide. Fine? So that's what we have discussed today. Fine? So practice those reactions, otherwise you will be finding P block like very difficult topic, because lots and lots of reactions are there. So practice as and when it is be taught. Fine? Thank you very much. Take care. Bye.